Alright, so in this video, I want to talk about work, energy, angular values of a dipole in an electric field. This video will be kind of complicated, and maybe this is just my opinion, but because it took me quite a bit of time to finally conceptually understand what's going on. So here I've written here a couple things to note from, classical mechanics, and that is work is equal to the sum of the forces over change in distance, right? In other words, the integral of force and then dot product R, or just dr. And since we are working in this kind of setup where we are talking about torques, right? So from the last video, I talked about the calculating or finding the torque value for a dipole in an electric field. We can say that the angular equivalent of force is torque. Oh, let me switch my color. Is torque, and the angular equivalent of the R is the angle. So in this case, phi. So thus, work can be defined as torque d phi. And so without further ado, let's derive what is the work done by the electric field on the dipole, right? So we know that work is equal to the integral of torque d phi, just like we just said. But now we need some bounds, right? And so here is where we'll need to recall something from calculus 1/2, and that is that if I have an integral from negative integral of a to b of f of x dx, that is equal to if we just change the bounds. So we switch the bounds from, instead of a to b, we switch from b to a. We would basically take out the negative. And you can derive this by, searching it up and whatnot. But this is not a math class. This is a physics class. So I'll assume that you already understand this concept. And it's one that you might have forgotten. So let's just say over here we have increments. So we have starting from theta 1 and increasing to theta 2, right? And then so on and so forth. So we can just say from theta 1 to theta 2. Those are our bounds. However, the torque, right? So on the positive charge, it will be kind of pushed this way. The negative charge will be pushed this way. And so the torque is moving in opposite direction to the way our angles are increasing. And so also recall that our torque for a dipole in an electric field is P, so the dipole moment, PE sine phi, right? But notice that the torque is moving in the opposite direction. So the torque is moving clockwise, and our angle is moving counterclockwise. So, that means we need to use this calculus formula that I just wrote out. And that is, we put a negative sign because our work done by the E field is opposite to the angles that we are writing down. So theta 1, theta 2, so negative the value of torque, which is PE sine phi d phi, right? And so now we can solve this. So using, a bit of basic calculus, what is the integral of sine? The integral of sine is negative cosine. And so this negative sign cancels out, which is quite nice. So we get PE cosine phi with bounds phi 2 and phi 1, which gets us to PE cosine phi 2 minus PE cosine phi 1. So let's stop and think about this conceptually. What this is saying is that the work done is the torque at this point minus the torque final. So like this, right? And this should make sense. The theta 2 is a bigger angle, and the theta 1 is a smaller angle. So and theta 1 and theta 2 can be defined arbitrarily. Theta 1 could be 0, right? And I'll discuss that shortly. And so now we have this other thing. So actually I'll draw this line here to make sure that we one side is the recall information, one side is derivation. Work is equal to change of kinetic energy, right? So, this is going this way, right? And change of kinetic energy is equal to negative change in potential energy. And so that means that we can say that the potential energy, U1 minus U2, right, as we've written here, is equal to PE cosine phi 2 minus PE cosine phi 1. And this should lead us to see something interesting here, and that is that if we just match the numbers here, so we have 2 and 2 and 1 and 1, so whichever arbitrary of choice, U is equal to negative PE cosine, oh, I forgot the S, cosine phi. Okay, so let's pause and think about this conceptually again, right? Our kinetic energy is decreasing as we increase or move this way, right? And that means that our potential energy would obviously, so kinetic energy is increasing this way as we are moving in the direction towards equilibrium, and that means our potential energy will become less, whereby our potential energy will be at a minimum when it is parallel with this electric field, right? But so then it makes conceptual sense, right? Because if it's parallel to the electric field, the angle will be 0, right? And cosine of 0 is 1, right? And so if we didn't have this negative sign here, it would indicate that it's a potential energy maximum. But it clearly isn't, right? Because it's parallel to this E field. So then you might ask me, then what happens if we have it exactly 180 to the field? So that is, initially we have it parallel, then it starts moving, then we put it this way, and then it's 90, and then it's 180. So at 180 degree, cosine of 180 degrees is negative 1. And so that means that if it's anti-parallel, right, so the positive charge is here and the negative charge is here, versus when it's parallel, where the positive charge is here and the negative charge is here. So when it's anti-parallel, it will be at a potential energy maximum. And so these are some important values to note, and that is that I'm going to draw this kind of coordinate system, and then the E fields kind of run this way. And that is that the potential energy at this angle of pi over 2 or 90 degrees or whatnot, so I'll say angle at 90 degrees, potential energy at 90 degrees will equal to 0, right? Because cosine of 90 is 0. And so that's like kind of the halfway point. When it's parallel, so cosine of, or potential energy cosine of 0, it'll be equal to negative 1. And then at this point, it will be a maximum. At 180 degrees, it will be equal to 1. And so that should make some conceptual sense, right? It's kind of moving, kind of opposite to the direction of our torque due to the electric field. And thus running anti-parallel, I have to repeat this very many times, running anti-parallel, you have a potential energy maximum. Running parallel, it will be a potential energy minimum, right? And both of them are parallel, but the only difference is that a tiny perturbation here will kind of cause this dipole to swing quickly over, versus a tiny perturbation when it's parallel will cause it to swing a little bit and then oscillate backwards really quickly. So, thus you can easily conceptually understand that. So now, tangentially to this, we notice that it's PE cosine theta, which looks very similar to our ideas of dot product. And that is just it. That is that the potential energy is equal to the negative dipole moment vector dotted with the electric field vector. And so these are all helpful formulas. It will just depend on the problem at hand that you will require to use it. So that is that torque is equal to P cross E, right? And that's one formula. And then potential energy is equal to negative P dotted with E. And so I think that is about it in terms of understanding these situations. Naturally, of course, the last thing is angular values, and that is because we can describe the potential energy difference, right? U1 minus U2 is equal to kinetic energy, right? So U1 minus U2 is the negative change of potential energy. And since this is a torque situation, you'll have angular values. So you would get 1/2 I, the moment of inertia, times the angular velocity squared, and then minus the initial, right? And so these are all from equations from classical mechanics, whereby this side is, notice it's W2 to W1, right, or W2 minus W1. So this is indicating its kinetic energy. So it will just depend on the problem, whereby which formulas you need to use and which concepts you need to use. But I still stress that you need to understand this idea of potential energy maximum, potential energy minimum, and potential energy minimum is a -1 value. The halfway point is 0 and 1. So all proportional, of course, depends on the E, field values and whatnot. And so that's all.